Hello everyone, my name is Rohan Gawande and my team member is Karthik Patekar. I am presenting our embedded system project titled Microwave Oven, developed as a part of the Emertexe embedded system internship. Through this project, I work on understanding how a microcontroller is used to control a real-life appliances by integrating hardware and embedded C programming. This presentation explains the design and working of a microwave oven using embedded system concept. This slide explains the technical competencies gained during the internship. It reflects a strong foundation in C programming, including control structures, arrays, pointers, functions, and string handling. Along with software skills, the internship also provided knowledge of microcontroller architecture, embedded system, and peripheral interfacing and also memory organization. This slide 3 provides an overview of the topics covered in the presentation. It acts as a structural guide, starting from the basic concept of embedded system and moving towards the simulation environment, microcontroller architecture, interrupts, timers, and peripheral interfacing, and finally the complete project implementation. This flow ensures systematic understanding of the microwave oven embedded system. And the next slide is in this slide, an embedded system is a combination of hardware and software designed to perform a specific dedicated function within a large system. It operates using the input process output peripheral and is optimized for reliability, efficiency, and real time performance. Unlike general purpose system, it executes fixed program for a single task. Based on application requirement, embedded systems are classified as a standalone real-time network, mobile and based and mobile distributed systems. They are widely used in consumer electronics, automobiles, medical devices, and industrial automation. Memory is an embedded system is classified into RAM, ROM, and hybrid memory based on functionality and data retention. RAM such as SRAM and DRAM is used for temporary data storage, while ROM types like PROM, EPROM, and mask ROM store permanent programs. Hybrid memories, including flash, EEPROM, and NVRAM, combine volatility with reprogrammability. Embedded systems face challenges such as limited memory and processing power, real-time concentrates, and power consumption. Efficient input-output handling, testing, hardware-software integration, and code optimization are critical to system performance. A microcontroller is an integrated circuit designed to perform a specific control oriented task within an embedded system. It integrates CPU, memory, input output peripherals on single chip, resulting in compact size and low power consumption. Microcontrollers are optimized for dedicated application but have limitation in memory, input output resources, and processing speed. Selection of a microcontroller depends on application requirement, cost, performance, and availability of development tools. Additional features such as timers, communication interference, ADCs, that is analog to digital converter, also influence the selection. In slide 7, a microwave oven is an electronic appliance used to cook or heat food using high frequency electromagnetic waves called microwaves. The magnetron converts electrical energy into microwave energy which penetrates food and causes rapid vibration of water molecules. This molecular vibration produces heat, resulting in efficient and fast cooking. Microwave ovens operates in different modes such as microwave mode for heating, grill mode for browning, and convection mode for uniform cooking. The entire operation is controlled by an embedded control system for precision and safety. Pixim Lab is a simulation tool used for designing and testing PIC microcontroller based embedded system. It provides a virtual development environment that allows programming and hardware interfacing without physical component. Pixing Lab commonly uses the PIC 16F877A microcontroller. It has the core controller for simulation. PIC 16F877A is an 8-bit 40-pin microcontroller supporting multiple input-output ports and external peripherals. It operates up to 20 MHz clock frequency and is widely used for prototyping embedded application and learning. In this slide, a character LCD, that is CLCD, is used in embedded system to display alphanumeric characters and symbols. It commonly supports display formats such as 16 into 2 and 16 into 4 and is controlled using ASCII character codes. The CLCD contains an internal controller with ROM and RAM for storing characters, patterns, and instructions. Data is transferred through data lines, that is D0 to D7, along with control signal like RW, RS, and enable. CLCDs are widely used for user interfaces due to their simplicity and low power consumption. A tactile switch is a momentary push button device that provides a physical feedback when pressed. It is commonly used in embedded systems for user input such as mode selection and data entry. When pressed or released, the switch generates a digital signal for the controller. Due to mechanical contact behavior, the switch doesn't change state instantly and produce unwanted pulses. This effect is known as a switch bouncing. Now, my team member Karthik Patekar will explain remaining slides.
Hello everyone, I am Karthik Patekar. Now I am going to continue. So it's a matrix keypad. A matrix keypad is a compact input device used to accept user commands in embedded systems. It consists of tactile switches arranged in rows and columns to reduce the number of input-output pins required. The microcontroller detects a key press by scanning row and column lines and identifying their intersection. Matrix keypads are commonly used for mode selection, time setting, and parameter entry. They provide an efficient and reliable user input method for embedded applications. An interrupt is a signal that temporarily halts the normal execution of a microcontroller program. An interrupt service routine ISR is a special function that is automatically executed in response to an interrupt. The ISR handles the interrupt event and then returns control to the main program. ISR execution has higher priority than the main program, ensuring fast response to critical event. Interrupts improve real-time performance in embedded systems. A timer is a hardware module used in microcontrollers to measure time intervals and count clock cycles. Timers operate using the system clock or an external clock and are used to generate delays and periodic interrupts. The PIC16F877A microcontroller includes timer 0, timer 1, and timer 2 for timing operations. In this project, timer 2 is used for timing control and accurate time-based functions. Timer 2 is an 8-bit timer that supports prescaler and postscaler for generating periodic interrupts. Moving towards the buzzer, a buzzer is an audio signaling device used in embedded system to produce sound alerts. It provides audible feedback to notify the user about events such as completion, errors, or key confirmation. In this project, the buzzer acts as an alert indicator when the cooking time is completed. The buzzer is interfaced with the microcontroller through the GPIO pin. It can be controlled using timers or interrupts for precise sound generation. Embedded programming involves writing software to control hardware resources of an embedded system. The program is typically divided into source files and header files to improve modularity and code reuse. Initialization functions configure hardware settings before execution of the main application loop. The main program runs continuously using an infinite loop to perform the required task. And header files define function prototypes and configurations for proper program linking. Now let's see what we accomplished. So far we have executed as shown. As you can see the code, and we are using MPLAB X IDE. Version 6.15 is my version of MPLAB X IDE, and I have created a microwave oven project which has a head of file clcd.h main and matrix keypad, which also consists of a header file and a timers. And the timers that we are using in this is 4 by 4 matrix keypad, and it has the following source file also. So as you can see the code, and it has all the means that are required for the microwave oven. I am going to build it. Just a minute. Yes, the output is successful. So we can stimulate in the Pixim lab. Okay. So I am going to use the board of this Pixim lab, and I am going to use it as a PIC genus. So which has a, as you can see, it is a PIC 16F877A is the version of the microcontroller that we are using for this project. So I am going to load this hex file that we have coded in the MP lab from this document. As you can see, okay, that's how you have to do. So we have to use the hex file for the code running. So you can see the powering on of the microwave oven in the before slide. So right you so and once the oven is started, we have the four following modes, which is micro mode, grid mode, convection mode, and start out mode. So micro mode we have seen earlier why we have to use micro mode, grid mode, and convection mode, and start mode. So we going to see the execution part in this output screen. See, I am going to press the key 1 for the micro mode, and it has a power of 900 watts. So I am going to set the timer as per my cooking requirements, say 45 seconds and 2 minutes. Okay, let's enter. As you can see, the timer is started and the fan is running. Okay. So if you want to stop it, or else if you want to go for the other more, you can just stop it and go for the menu bar, or else if you want to resume it, and again you have to press the one micro mode and decide the time. It's up to you whatever the time you want to set. It is required, it's upon the timer. If you want to stop it or pause it, press switch number 5 such that you can see the fan is stopped and the heater is stopped, right? Okay, if you want to give an indication to the user, you can just simply press RB3. See, if you want to continue it, press 4 and you can listen sound. This is how the user is informed through a buzzer. Okay, now let's go for the previous session. For that you just have to stop this. Okay. What if I wanted to go for the grill mode? I just have to select the option number 2, and then set the timer. See, let's 12 second and 1 minute. Okay, see the timer is going to reduce initially, and then the fan and the cooler starts cooking. Okay, now let's go for the other mode. I am going to stop it, and then I am going for the convention mode. Here, what is convection mode, where the heater is preheated such that the cook can be, it is like preheated. So I am going to set an initial time temperature, say 45 degrees Celsius, and then I am going to enter it. So you can see right preheating time temperature. So this is how you get the output of a convection mode. And similarly, if you want to tell the user or else the owner of the like, you can do it with the beep. Okay, now let's go for the power on screen, and it has the following four modes: micro mode, grill mode, convection, and start mode. So which is followed by 900 watt power. Grill mode, we have to set temperature, and then we have to go for the other mode. In case of convection mode, as the oven is being preheated, it is going to take, ask you the temperature, and it is depends on the requirement, and then you go for the preheating. Once the preheating is done, you will be notified like it with a buzzer, and we going to send an alarm for the user. That's it. Now, once it is done, the door status can be notified to the user. Okay, so thank you. And at the end of the session, I wanted to say thank you for the Emertexe for letting us to know such a valuable information. And a word of thanks would be very much less for them. And thank you for this opportunity. And the outcomes from the project are very useful for us, and also the last few sessions from the workshop also made us understand what is the current situation for an electronic student in the outside world. And thank you very much for this opportunity. Thank you.